going to discuss instantons. And the plan is roughly today, well, this morning, during the first lecture, and probably part of the second lecture, we'll discuss instantons in quantum mechanics. Then the remainder of the second lecture today, we will discuss decay of the false vacuum. In QFT. And then tomorrow, we'll discuss the vacuum states of non-abelian gauge theories, the so-called theta vacua. That's where we're going. And we'll spend a fair bit of time on the instantons in quantum mechanics, because many of our results will directly generalize and be applicable to the quantum field theory cases that we're interested in. So instantons, what are instantons? So instantons are in the field theory case, they're field configurations that are localized in time. They're basically saddle points of the Euclidean action. And they can be used to study non-perturbative corrections to the path integral. So most of what we've been doing in QFT so far is perturbation theory. And as I pointed out several times in QFT1 and QFT2, the ordinary perturbation theory, the loop expansion or coupling constant expansion, gives us an asymptotic series, which means that we are missing any effects that go to zero faster than a polynomial in in h bar or in the coupling constant. So for instance, there's no way in perturbation theory to see an effect that scales like e to the minus 1 over h bar in the semi-classical limit. And so over the next few lectures, we're going to learn how to compute some of these effects. So a familiar example of a non-perturbative effect that you're all used to, all have seen before, is tunneling in quantum mechanics. So, for instance, we could have a particle with unit mass in some one-dimensional potential that might look like this. And we have a particle of energy E. And classically, there's no way for it to move through the barrier. But of course, quantum mechanically, there is. And the way you're used to probably finding the transmission rate or tunneling rate is by the WKB approximation, where you find the wave function in each of the classically allowed regions. So if Q is greater than Q1, less than Q1, or greater than Q2, then particle has enough energy to be in that region. So we can solve the Schrodinger equation in these regions, and it'll be some oscillating wave function will just be some oscillating function, and it will decay exponentially in between. And so the WKB approximation is just basically solving for the wave function in each of the classically allowed regions and the classically forbidden regions and matching them together. And the result is that the transmission amplitude is takes this form. And there'll be some corrections to this, which can be computed systematically. So this is a non-perturbative result. If we treat 1 over h, if we treat h bar as a small parameter, then the Taylor series for this will just vanish. There's no non-zero terms. So we'll never see these kinds of effects in perturbation theory. So this is by far the easiest way to solve this problem in quantum mechanics. And in some cases, you can do the same thing in quantum field theory. You can find the wave functional for field configurations and match them together in classically allowed and classically forbidden regions. But generally, this is only feasible if the problem has a lot of symmetry, and even then, only probably approximately. So we're going to develop a new method that will let us, it will be more difficult to apply to quantum mechanics, but will generalize much more easily to quantum field theory. And so the new method is the method of instantons. And so what we're going to be studying is a Euclidean path integral. And we're going to look at the transition amplitude from some initial position eigenstate to some final position where the transition takes a Euclidean time, t. Okay, so we'll see in one of our examples when we're studying this object that if we're trying to compute this using the saddle point method, our saddle points are instantons. So there'll be solutions to the Euclidean equations of motion that are only have non-trivial dynamics for a short amount of time. And so we'll see that in some of our examples. But it's worth pointing out before we go through those examples that there's a lot of information contained in this expression. So we can write this as a Euclidean path integral. So the boundary conditions are x of minus t over 2, it's xi, x of t over 2, it's xf. Then we integrate over all x of the Euclidean action over h bar. So one thing we can read off from this amplitude is the ground state energy. And to see that, we can insert a complete set of states. So call the energy eigenstates n. Say they have energy En. So if we insert a complete set of states, we get that xf e to the minus ht over h bar xi is e to the minus en p over h bar xf n xi. So in the t goes to infinity limit, we can just read off the ground state energy from this. So E naught minus the limit t goes to infinity, h bar over t log z. And if the potential is unstable, the ground state energy will pick up an imaginary part. And so it can also, if we're interested in tunneling, we can read off a decay rate from the same path integral. It's just the factor 2, the imaginary part of the ground state energy. Okay. So we want to study this path integral in the semi-classical limit. And the easiest way to do that is using the saddle point approximation. So we want to expand or approximate this, this integral by saying the contributions to this integral are dominated by the saddle points. And so if we just find the saddle points, places where the Euclidean action is stationary, we can find an approximate expression for this path integral. And so the saddle points will satisfy the equation, the variation of s with respect to x is 0, which is just minus d squared x bar dt squared plus v prime of x bar equals 0, where x bar are the saddle points. And so then we can expand Euclidean action around saddle points. And what we get is this expression, where x is x bar plus x tilde, our function is the time. And this is using the same notation we introduced in QFT2, so this is just the integral dt1 dt2 x tilde t1 times the second functional derivative of s with respect to x of t1 and x of t2. So this expression probably looks familiar to you. This is very similar to what we did in QFT2. So we can perform the Gaussian integrals, and then we'll get that z is some normalization times the determinant S double prime evaluated at the saddle point, the minus a half times e to the minus se of x bar for h, and in general be some order h bar corrections to this formula. So we could do this. So if we only keep the second order term, this is just a Gaussian integral, and we can compute this just by discretizing the path integral in the usual way.
One question then. How did you get that decay rate is like related with E0 like that?
Can you repeat that?
I mean, how do we get this expression for the decay rate, like related with the ground state energy?
Oh, okay. So I didn't derive that, but you can imagine that if the energy has an imaginary part, so if the ground state energy has an imaginary part, in real time, we'll have e to the, it will evolve like e to the I e naught t over h bar. Some state will evolve. And if e naught has an imaginary part, then we'll have some decay of the amplitude. It will not be, if we compute, say, the state 0, 0, this will have a time dependence. And so there'll be some decay out of that, and we can imagine that's to some part of the system that we're not including when we're quantizing the theory. So this would, if this has an imaginary part, this would go like e to the minus the imaginary part of e naught t.
Isn't there a decay in x? Like, doesn't the amplitude decay with position instead of with time? I mean, looked at a certain point, there's a particle that flows in and hits a potential, and part of it goes through, and part of it comes back. So if you stand still at a certain position, then in time the amplitude is going to do this, and then a little bit back on the left and on the right. From your potential, it's going to like have a little bump. It's not going to decay exponentially.
So you can imagine we've got a potential that looks something like this, and we can ask what's the probability that it's going to be in some region around this local minimum, and that will decay exponentially. If you have a potential that's like this, you compute the ground state energy, and it'll be some real number. If we deform the potential and compute the energy of that same state, of the ground state energy of the original potential, that will pick up an imaginary part. It will tell us about the decay rate of a particle that's...
Can you write down the Hamiltonian?
So I'm just considering the Hamiltonian corresponding to that Lagrangian up there at the top of the board. Just the Hamiltonian.
Just a kinetic term, which is Hermitian, and a potential, which is Hermitian.
Yeah.
So an energy cannot be imaginary.
if
Like the ground state is not gonna be the particle is there. Because part of it can run away, right?
yeah, this
It can
potential with a
energies.
potential unbounded from below has no ground state. So, but you can consider
So what's
this.
E0?
E0 is the energy of the. So you can, in the unperturbed potential, you can find the ground state that has some real energy. And if you change the potential to make it unbounded from below, you can compute the energy of that same state, and it will pick up an imaginary part. We'll come back to this later when we talk about. Okay. So for the immediate, our immediate purposes, we're just going to be considering real energies. So let's study a very familiar problem from a slightly unfamiliar perspective. So let's look at the harmonic oscillator and try to compute the ground state energy using this method. So this will be, along the way, we'll derive some useful results that will be applicable when we study instantons. So we'll get to that very shortly. So what we're interested in studying this potential. But if we look at our equation for the saddle point, we see that solving that equation for the saddle point is the same as solving the classical equations of motion for a particle moving in a potential minus v. And we're interested in computing the ground state energy. We can choose any initial and final position we like. And so the easiest choice is to choose xi equals 0 equals xf. In that case, since we're solving for the motion of a particle of unit mass with this potential, the only possible solution is that x bar is 0. And the Euclidean action of that solution is just 0. So all we need to do is compute the determinant. And we can compute the determinant in this case just by computing the product of the eigenvalues. So first of all, S double prime is just minus dt squared plus omega squared if choose v of x to be 1/2 omega squared x squared. And so these lambdas are the eigenvalues of this operator. And so what we want to do is solve this equation. For both the eigen functions and, well, what we're interested in is the eigen values at this point. And we want to solve this equation with the boundary conditions corresponding to our initial and final positions of our particle. So we should have that the particle starts and ends at 0. And this is not a difficult equation to solve. Get it's just 2 exponentials we haven't imposed the boundary conditions yet, but just the general solution to that equation takes this form. And if we impose the boundary condition at minus t over 2, we get A is equal to minus B. So psi lambda n, T is A sinh root omega squared minus lambda n equals T over 2. And second boundary condition can be used to find the eigenvalues. And they just take this form. Omega squared plus n squared. So we want to compute this product of all the eigenfunctions, but there's one thing we haven't considered yet is the normalization of our path integral. And because these products of the determinant depends on the potential, and it'd be useful to make a choice of normalization so that the normalization is independent of what potential we choose. If we make the choice that n squared is proportional to the determinant over the zeroth eigenvalue, zeroth eigenfunction evaluated at psi over 2, and we make some choice of the normalization of the zeroth eigenfunction, then n will be independent of v. This is a consequence of the Gelfand-Jageln theorem that you did the optional problem in QFD2 you saw.
Where does the first equation come from? The n squared?
This?
Yeah.
So this is a choice we can make. N was just a normalization. We're free to choose it however we like.
Okay.
we choose it like this, then n is independent of v. So if we want to study a more general problem than just the harmonic oscillator, like we will in a minute, if we make this choice, then we've chosen n once and for all path integrals. So convenient choice. So this fixes A to be 1 over omega. And so we get that n times the determinant minus a half is just omega the limit as t goes to infinity, which is all we really care about, because if we want to compute the ground state energy, we want to take the limit that t goes to infinity to get rid of all of the other terms here. So we get omega over pi h bar to the half e to the minus omega t. Just one term in this inch will contribute in that limit. And we can then find the ground state energy minus limit t goes to infinity, h bar over t log c, which is the half omega h bar. No surprise there, but so this is a very complicated way of deriving a very familiar expression. Okay, so let's apply these techniques to another case, double well, and here we'll see that instantons provides the most important contributions to the path integral. We're interested in doing a saddle point approximation. So here we're going to study a symmetric double well potential. The potential has two minima at plus and minus A. And we want to choose d of x to be even. And let's say that the second derivative at both of the minima is omega squared. So it looks like a harmonic oscillator near plus or minus A. And so then what we're going to need to do is we're going to need to solve the Euclidean equations of motion, which are just like the regular equations of motion, except the sign of the potential flips. And so again, we're going to, our goal is going to be to try to compute the ground state energy. So here, and we'll also compute the splitting between the entities. So classically, this has two degenerate minima. And so quantum mechanically, you expect that those classical minima are the degeneracy between them is lifted. And so what we'll find is that the energy of the two lowest states are approximately the same as the harmonic oscillators. So the first approximation, it doesn't matter what's going on over here. We'll have states that we'll have two states that are similar to the ground state of the harmonic oscillator, but those will not be energy eigenstates. We'll have to take linear combinations of those, and even and odd linear combinations of those will be the two lowest energy states, and instantons will provide the dominant contribution to the energy splitting between those. That's what we're going to find. So what we're interested in is computing is, again, the ground state energy. And again, we'll try to compute an amplitude for a particle to go from minus A to A in a Euclidean time t. And so what we need to do is solve the Euclidean equations of motion. And a useful observation we can make is if we're solving this equation, the energy, 1/2 dx bar dt minus v of x is a constant of motion. And so there should be a solution of the classical equations of motion with zero energy. So there's no friction term. So if what we're interested in looking at is a particle that starts here and goes here. And since these have the same potential, there should be a solution that has zero energy that goes from one to the other. And so if there's a zero energy solution, then we only have to solve a first order equation instead of a second order equation. We set E equals to 0, tells us that dx dt is root 2v of x bar. And for large t, or large positive or negative t, we can solve this approximately. So for large t, for large t, the particle is near A. So we can Taylor expand v of x. And what we get to v of A, which is 0, plus A minus x bar, v prime of A, which is also 0, because that's a maximum of the, or maximum or minimum. A maximum here, a minimum here. And so the first term that survives, the quadratic term. So this is approximately A minus x bar omega, which tells us, just integrate this equation and get that A minus x bar is approximately e to the minus omega t for large t. And similarly, for e less than 0, t large, then the same logic tells us that x bar plus a is e to the omega t. So from this, we can figure out what our solutions to the Euclidean equation of motion should look like. So for t large, the solution should be exponentially close to a. And for t large and negative, solution should be exponentially close to minus a. And somewhere in between, it should rapidly cross through barrier. So, and we'll reach 0 at some time. Let's call it the time where it reaches 0, t1. And so this is our instanton. This is an instanton with center t1. It's localized in time. So in the large t goes to infinity limit, our boundary conditions just go to the far past and far future, and that won't really change the form of the solution near the center. So for just a short time of order omega inverse is our saddle point solution different from a or minus a. So it's localized in time. And that's where the name instanton comes from. So, only exists for an instant. And if we were interested in computing the amplitude to go from a to minus a instead of minus a to a, we would have a similar solution. That just went in the other direction, and this is called the anti-instanton. Okay. So in order we need two things now to do the saddle point approximation. We need to find the Euclidean action, and then also the determinant, the prefactor. So let's find the Euclidean action first. So the action of one instanton or anti-instanton is, let's call it S naught, the integral from minus t over 2 to t over 2, f the x bar e squared plus v of x, which change our integration variable from et to x. Okay, so we computed the Euclidean action of one instanton solution. But if we actually have infinitely many one instanton solutions, because the action doesn't change if we change the center of the instanton. So there is, we should account for, include all of the instantons with all possible centers in our semi-classical approximation to the path integral. So we need to integrate over the location of the centers of the instantons. And then here we've got some normalization. Which will be closely related to the normalization that we found for the harmonic oscillator.
Then, can you repeat again why is that we are considering instanton, like center in different places, in different times?
In different times.
Yeah.
So T1 here is the location of the center of this instanton. And this is a solution to the Euclidean equations of motion. So is a different solution with a different center. So the blue line is also a solution to the Euclidean equations of motion. And so if we are doing a saddle point approximation, we should sum over all possible saddle points. So these are different saddle points.
Okay.
And here we've got a continuous set of saddle points. So we should include all of them.
But how do I know that, like, because to solve the equation we saw the, if you want, limits for large P and large negative T.
Yes.
And then we said, okay, this has to cross our T equals x equals 0.
Yes.
It has to cross it at some time. But I could argue that, oh, maybe just one of those is the actual real saddle point. How do I convince myself that just by looking at the asymptotic behavior of the solution, and I had like this freedom of choosing where do I cross? Maybe just crossing it.
Another way to see it is that there'll be a, so this is a direction in function space, the function x of t, that doesn't change the action. So if there's a direction in function space where the action doesn't change, that means there'll be a 0 eigenvalue.
All right.
And so you can explicitly show that by computing the eigenvalues of s double prime, and you'll find that there's a zero eigenvalue. So integrating over this is basically accounting for that 0 eigenvalue. There's a direction in the set of set of configurations x of t that don't change the action.
Isn't that like similar to a gauge?
In some way, in the sense that gauge equivalent configurations have the same action. Yes. And so this k then is proportional to the determinant of S double prime to the minus a half with the zero eigenmodes, zero eigenvalue removed. Because we've already essentially taken care of that by integrating over the locations of the centers of the instanton. But these are not all of the saddle points. There are more. So to see that, you note that the instantons are localized. I argued that they're localized. They have a size of order 1 over omega. So one instanton solution corresponds to tunneling once from minus A to A. But there's no reason the particle couldn't tunnel back and forth multiple times. So it could go from minus A to A to minus A to A as many times as it likes. So we need to account for the multiple tunneling solutions. And so there'll be approximate solutions to the Euclidean equations of motion with finite t. That look like this. So we'll start out at minus A and very quickly go to plus A, stay there for a long time, go back to minus A, and do this several times, eventually ending up at A. So these solution, so that these are approximate solutions of the Euclidean equation of motion, because we get exponentially close to plus or minus A. And so we can just imagine stitching together this with an anti-instanton. And these become exact solutions, and they can become stationary points as t goes to infinity. So to do a consistent saddle point approximation to this amplitude, we need to include not only the one instanton solutions, but also the n instanton solutions. And from looking at this sketch of the n instanton solutions, so we notice that except for small intervals, v double prime is omega squared, because the solution sits very near plus or minus A for most of the time, which it has to for this to work. So if we try to put together an instanton and an anti-instanton and put their distance to be less than 1 over omega, less than the width here, it doesn't work. So we have to get close to AA before we can stitch this solution together with a minus instanton. So we've implicitly, so these solutions exist if the separation between the instantons and anti-instantons is big. So this is the so-called dilute gas approximation. The instantons are widely separated. So we're almost done with this problem, but I don't have time to finish it in the last 2 minutes. So we'll resume in about an hour and go through and compute the finish computing this amplitude by including the contributions of these n instanton solutions. Any questions?